Okay, so today we're learning about continuity. So in order for a function to be what we call continuous, basically you can draw the function without lifting the pencil. That is the most basic definition for continuous. So if you can draw it without having to lift it, it's continuous. So you could have like a polynomial, right? Or you could have, well, basically polynomials. You can't have things where you have like a hole because you would have to skip over that hole as you're tracing it, right? And you can't have things that go to infinity because you'd have to lift your pencil to go to the other side. All right, are you all on section 7? Yes.
What if we use pen?
Yes, pencil or pen, right? Okay, so the formal definition of a limit, the one that you will need to know for the AP Calc exam, so whenever it says show that something is continuous, this is what you're doing. So it says the limit as x goes to a of f of x is equal to f of a. So what that means, you know, for a limit to be equal to something, it means that as you go from the right and the left towards a certain thing, right, as you go towards a, the point is the same from the right and the left, right? So we're going a step further. We're saying not only does the limit exist, but it's filled in at that point. Okay, so as I go from the left and the right, I'm going to fill it in. So kind of like this and this. Yes, they meet, so the limit does exist, but it actually equals f of a. All right, so if something's not continuous, we use the word discontinuous. Geometrically, a function is continuous if there's no break in it. So there's no vertical asymptotes, there's no holes or anything like that. So using the graph of f below, at which numbers is f discontinuous and why? So it's going to be discontinuous at this x value, and this x value. Okay, so it's going to be at x equals, I think it's -6. At x equals 0 and at x equals 5. Okay. And the reasons that it is discontinuous, so at -6 is because there's what we call a jump. Oops. Jump. So it jumps from one y value to another y value. Okay, so that's a jump discontinuity. And then the same thing at 0, that is also a jump discontinuity. And then at 5, what do you think we call the one at 5? Right, a hole. So we've learned that before. In calculus, we sometimes call a hole a removable discontinuity. Okay, so it's removable because basically as we're drawing the curve, we could remove that discontinuity by simply filling in the hole. And we'll talk about something called a continuous extension in a little bit, like actually filling in the hole with a piecewise function. So number 2, so it says, where are each of the following functions discontinuous? So we have f of x equals x squared minus x minus 2. So if I factor, I get x minus 2 times x plus 1. Right, and we see that the x plus 1s then cancel. So we know from Algebra 2 pre-calc that that means that there's a hole there. So it's going to be discontinuous at x equals -1. Okay, like I said, because there's going to be a hole. Okay, if you look at the graph of the next one, we have 1 over x squared, which looks like this. So if we just had 1 over x squared, we wouldn't have a point at x equals 0. There's nothing there. But then this piecewise function says we do have a point at x equals 0. We have the point 2, 0.2. So that's what the graph looks like. So are you able to draw this without lifting your pencil? No. Okay, so this is discontinuous at x equals 0. And this one would be what I would call an infinite discontinuity because it goes to infinity. It's also kind of like a jump, like it jumps from one value to another, but infinite because there's no like point up there. All right, so part C. So part C, if you look at the function, if you have x minus 4 all over x squared minus 3x minus 4, it factors into x minus 4 times x plus 1. So we see that we do have a hole. And our simplified version is 1 over x plus 1. So if I was graphing the first part, I would know that it looks like 1 over x, except it's been shifted to the left 1, right? The vertical asymptote, instead of being at 0, it's at -1. All right, so you get that? All right, so we are going to have something like this and something like this. But at x equals 4, it says we don't have the point on the curve, right? So that's going to be open. So that's what the first part of the piecewise function says. All right, and the second part of the piecewise function says, well, f of x is equal to 1/5 when x is equal to 4. Okay? So let's think about this. On that original hole, do you guys know where that hole is located? 4 comma what? What's its y value? So plug it into the simplified version. Yeah, Chloe? It is 1/5, right? So that hole is located at 4 comma 1/5. So what the second part of this piecewise function is saying, it's saying to fill in that hole. Okay, so we're going to fill in the hole, and it's now continuous there. Okay, so its hole has been filled in. By the point 4 comma 1/5. So by that second part. Okay, so it's now continuous at that place where there was originally a hole. It's continuous there now. Okay, so where's the only place where it's not continuous? At x equals -1, right? So that was the infinite one. All right, and then the next one we have is the greatest integer function. Just remember this from Algebra 2, called a step function. So the greatest integer function says that we have the greatest integer that is less than or equal to a certain number. I sometimes call this the floor function, meaning you round down. So if you have 1.5, it rounds down to 1. If you have 1.9, it rounds down to 1. 1.99 rounds down to 1. But once you get to 2, you have 2, because less than or equal to, right? Every integer greater than or equal to. And then you have 2.1, it rounds down to 2. 2.3 rounds down to 2. Okay, so we're going to have filled in on the left, open on the right. Filled in on the left, open on the right. It's going to look like that. Okay. Andy. All right, so where is this one discontinuous? Everywhere what? It's not everywhere. It's continuous at like 1/2. At 1, 2, 3. Yeah, so it's discontinuous at all integers, right? So we call those integers. 1, 2, 3, -1, 0, -2, and so on. Okay. So there's the little definitions that I already talked about. So removable discontinuity or a hole is removable if it can be made continuous by filling in a certain value. So if you can fill in the hole, we call that the continuous extension. So it's like making a piecewise function, kind of like part C, where we filled in the hole. Okay, a jump discontinuity. It says if the left and right hand limits at x equals a both exist but are not the same value, then the graph jumps. So as I'm tracing from the left, I go to a certain value, and as I'm tracing from the right, I go to a certain value, but they're not the same value. Okay, and then an infinite discontinuity. It says it's infinite if as you approach a, f of a goes to infinity or negative infinity. So you can put plus or minus there. So in other words, there's a vertical asymptote. All right, so it says just like when we learned about right and left hand limits, we can have right and left hand continuities too. Okay, so this is a little bit weird. So continuity from the right. It says a function f is continuous from the right if you take the limit as x goes to a from the right of f of x, and you end up getting f of a. So it looks like the continuous definition, except it has the little plus sign to the right. So graphically what this would be is basically you're tracing along a curve, and on the right side it's filled in, but on the left side it's open. Okay, so we would call something that looks like that continuous from the right, because the right-hand limit exists, and it is filled in at that point. Okay, continuous from the left is just the limit as x goes to a from the left of f of x equals f of a. So a graph of that would be as you come in from the left, you get a certain value, and it's filled in, but the right is not filled in. So we would say continuous from the left. So it says, where is the function continuous from the right and continuous from the left? Okay, before I do that, let's just talk about where it's not continuous first. So where is it discontinuous? Yeah, so at x equals -3, what kind is that? It's a jump, right? It jumps from one to another. All right, x equals -1. What kind is that? Infinite. It kind of looks like they join, but they don't. It's a vertical asymptote. And then x equals one more? 2, exactly. So x equals 2. And what's that one? Nope, that one's actually a whole. And it's kind of tricky, but the definition of a jump says that the limits from the left and right exist, but they aren't equal to each other. So in that case, they are equal to each other. They go to the same thing. Okay, so they're not at different heights. So it's actually just a whole. All right, so where are any of these continuous from the left or the right? Are any of them continuous from the left or the right? So how about -3? Is it continuous from the left or the right? Right. Are any of them continuous? So what about -1? Is it continuous from the left or the right? No, because it doesn't equal something, right? And then 2? No, right? So none of the other ones are continuous from the left or the right. So really, when you're talking about continuous from the left or the right, you often will say, where is it discontinuous first? Now, I could actually, if I asked you where something's continuous from the left or the right in this graph, I could actually say it's continuous from the left and right at 1, right? Because the limit as x goes towards 1 from the right is equal to its value, its y value, and the limit as I go from the left is equal to it. So it's actually continued from both the left and the right. Okay, so it's kind of confusing the way I worded it originally. That's why I wanted you to do discontinuous first. All right, so number 1. So it says, how should this function be defined to remove the discontinuity at x equals 3? Sorry, discontinuity is like such a tongue twister for me. I have a hard time. All right, so I'm going to factor. So I'm going to have x plus 7, x minus 3, and x minus 3. I cancel. So my simplified function is just x plus 7. So if I'm creating a piecewise function that removes the discontinuity, the first one looks the same way. And we say if x is not equal to 3, because it's undefined at 3. And the other part, we need to define where we want 3 to be filled in. So we want it to be what we call a continuous extension. You want to be able to draw this, and originally there was a hole, but with the piecewise function, we want to fill in the hole. Okay, so at 3, where do you think the y value should be? 10, exactly. You're plugging into the simplified version. So when you plug in 3, you get 10, right? So that means that we want 10 for what we call the continuous extension. Okay, what this does is it actually makes our function into the simplified version. It makes it the same as just x plus 7. So this is now equivalent to f of x equals x plus 7. It became the same function, okay? Because we removed that thing. We made it not a whole anymore. All right, is this making sense? All right, so every limit law that we had before applies to all of the continuity laws. So it says if f and g are continuous at x equals a and c is a constant, then the following functions are also continuous. So some number times f of x, like 2f of x, right? The sum and difference, if you have f plus g of x, it's also continuous if f and g are both continuous. And the difference, the product, and the quotient. All right, and like I said, these all follow from the limit law. So I'm going to show you one of these. You don't need to know this on the test, but it's kind of good to see like where these come from. So if I want to show that a product f times g is continuous, if I know that f and g are both continuous, in order to show something's continuous, we need that limit or that definition of continuous. So whatever the test, and the test will ask you this, it will say, using the definition of continuous, show that this is true, right? Or show that it is continuous, right? So if you're going to show that something's continuous, we want to show that the limit as x goes to a of the product, in this case, f of x times g of x, is the same as f of a times g of a. We want to be able to just plug in a into the formula, into the functions. So that's what we're trying to show with this proof. Okay, so what we start out with is f and g are continuous. We were given that. So we know that. So if we start with the limit as x goes to a of f of x times g of x, by a limit law, you can bring that limit in. So you can say, well, that's equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x by limit laws. We know we can bring limits in. But since f and g are continuous, the definition of continuous says that the limit as x goes to a of f of x equals f of a, right? So this whole part becomes f of a. And the other whole part becomes g of a. And that's what we wanted. So then we're done. Okay? So it's kind of a weird proof. It's just like, yes, because by limit laws, basically. All right, so we've talked about the direct substitution property. That was a really easy one that said if we want to calculate a limit and it's defined at that place, then we can just plug in the number. So if 3 doesn't make it undefined, then just plug in 3 to find the limit as x goes to 3. Okay, so that said that the limit as x went to a of f of x was equal to f of a. It was the same definition for continuous. So it says, therefore, any polynomial is continuous everywhere, and any rational function is continuous wherever it's defined. Okay, so it's kind of just like finding the domain. If you can find the domain, it's going to be continuous on that domain. Okay, so here's some examples. Well, these are the direct substitution examples. So this one just is a direct substitution. You can just plug in 1. That looks like 14. So you're going to have 1 to the 4th minus 3 times 1 squared plus 5. We know we're able to do this because 1 doesn't make it undefined. So you get 1 minus 3 plus 5 all over negative 4. So you get negative 3/4. And then another direct substitution property, it works for trig functions as well, as long as it's continuous at that point, or as long as it's in the domain, I guess. So if I plug in theta equals 0 to cosine theta, what's cosine of 0? 1, right? So that one's 1. And then sine of 0 is 0, right? So that's the same as just plugging it in. It's fine. So you're allowed to do that for polynomials, rational, radical functions, and trig functions, as long as the number you're plugging in is in the domain. That's all it's saying. So it says on what intervals is each function continuous? So this first one, it looks really weird, right? Because it's raised to the 2000. But what type of function is that? Is it a polynomial, rational, radical, or trig? It's a polynomial. It's a really big polynomial with the 2000, right? But it is a polynomial. And polynomials are continuous everywhere. Okay, so it's continuous on negative infinity to infinity. There's nowhere that's making it undefined. There's no square roots, there's no denominators, right? So it has to be continuous everywhere. We always say polynomials are smooth and continuous. Smooth means no sharp points. All right, so next one, where is it undefined? X equals 4 and negative 4, right? We can't have 4 or negative 4. So it means it's going to be continuous everywhere except at those points. So you can say continuous everywhere but x equals 4 and negative 4. Okay, or you could write it in interval notation and say negative infinity to negative 4, union, negative 4 to 4, union, 4 to infinity. So you're just skipping over the negative 4 and the 4. All right, and this one's a little bit harder. So we know that x can't be 1 and x can't be negative 1 as well. What else can you not have for x? Negative numbers, right? So x also has to be greater than or equal to 0. So we need all of those things to be true. So if you think about it on a number line, we know that we're greater than or equal to 0. We can't be negative 1, which we couldn't be anyway, right? Because we're greater than or equal to 0. And we can't be 1. So we're going to fill in everything except for the 1 from 0 on. So it's going to look like bracket 0 to 1, union 1 to infinity. So it's continuous on all of those places. All right, so the ones that the AP test does ask about all the time. I mean, it's important to know all these basics about continuity, but the ones that they will have all the time are things like this. So it says, what is the value for a that makes the piecewise function below continuous? Okay, so you always have to think, well, what does it mean for something to be continuous? It means that the limit as x goes to 2 or whatever is equal to f of 2, right? You can just plug it in. So in this case, we actually have the limit as x goes to 2 from the left. We want it to equal the limit as x goes to 2 from the right, right? Because we want for this not to be a piecewise function where there's a jump discontinuity. We want for this part, the second part, to be right there and fill in the other part. Does that make sense? We don't want them to be separate. We want them to be filled in, okay? This is cool. Do you like how I'm moving it? All right, so we want for them to match up from both sides. Okay, so we're going to do that. So as we plug into 2 for x into the first one, we get a times 2 squared plus 3 equals 3 times 2 minus 5. So I get 4a plus 3 equals 6 minus 5. So I get 4a plus 3 equals equals 1. So I get 4a equals negative 2, so a is negative 1/2. So if a is negative 1/2, then when you plug in 2 for both of the sides, you're going to get them matching up and being at the same value. Does that make sense? Okay, so sometimes these get a little bit harder. Sometimes you have a and you have b. So you have to find multiple variables. Okay, so that's what this one does. So you might want to write a little tiny for this one. All right, so what I was telling the last class is you actually don't need to write this first part here. You can just skip to right here most of the time, okay? Except on ones like this one, okay? Because I can't just plug in 2 into this first equation. Do you see what happens when you're plugging in 2? Right, you get 0 over 0. That's not what we want. Okay, so what we do is we do the limit as x goes to 2 from the left, because it's x values that are less than 2, of x squared minus 4 over x minus 2. That has to equal the second one. So we're setting the first one and second one equal to each other as we take the limit as x goes to 2. So now I can plug in 2 to the second one. So I can say a times 2 squared minus b times 2 plus 3. You see how I didn't have to write limit on that one? I could just go ahead and plug it. All right, so when I factor, I have the limit as x goes to 2 from the left. I factor into x plus 2 and x minus 2. So the part that was undefined with the x minus 2 now goes away. And the right side becomes 4a minus 2b plus 3. All right, so when I plug in 2, I get 4. So I have 4a minus 2b plus 3 equals 4. So let's just get all the numbers on one side. So I have 4a minus 2b equals 1. Okay, so I can't solve for a and b yet. Okay, so right now we were saying that the left side and the right side, when we go towards 2, are going to match up. We just made that happen. But we also need for the left side and the right side at 3 to match up as well. Okay, so now we deal with the 3. So looking there, when we find our equation, we're going to say, okay, I'm going to plug in 3. So I'm going to have a times 3 squared minus b times 3 plus 3 has to equal 2 times 3 minus a plus b. So we get 9a minus 3b plus 3 equals 6 minus b, or minus a plus b. And let's get all of our a's on one side and all of our b's on the same side. So I'm going to have 10a, what do I get? Minus 4b equals 3. Is that right? Okay, this goes back to algebra 1. What do we do now? Elimination. Yeah, so you can do substitution or elimination. So you have 2 equations that have a and b, and you want to solve for both a and for b. Okay, so we're going to line them up. So we're going to have 4a minus 2b equals 1, and the other one is 10a minus 4b equals 3. So I'm going to multiply that top equation by negative 2. So I get negative 8a plus 4b equals negative 2, and I have 10a minus 4b equals 3. And when I do that, I get 2a equals 1, so a equals 1/2. And then when you plug into the other one, you also get, so I'm just going to write etc. So you guys know how to plug in a to get b. You end up getting b equals 1/2 too. So I'm not going to do that stuff. But you can plug into another one. All right, so that's where we're going to stop for today. So you guys can start your book problems, not right now, but you have book problems to do, right? So you can start those, but you're not going to finish them until we have Labor Day off, so Tuesday. Okay, so they're not actually due till Tuesday. All right.